You're leaving? Okay, just remind me. Okay, because we are a bit late getting started. Okay, let's get the slideshow from current slide then. And let's, don't know of any major announcements now, so everything seems to be sort of smoothing out, I hope. There was something I was going to bring up, but I can't remember what it is now. So, any questions on anything we've covered so far? Okay. All right. We're at on in Chapter 2, Section 2.3. We just finished that last time, but we didn't have a chance for the vocabulary, so let's hit the vocabulary fairly quickly here. Two forms of the division algorithm are shown below. It says identify and label each term or function. Okay? And I hope most of you have your book, but if you don't, when they write it this way, f of x is equal to d of x times q of x plus r of x. Okay? What would you say the f of x was there in division? Remember how we used to give names to all the characters in the division? What would f of x be called? You earn it on, say again? Okay. In this course, f of x is always right, y is right. But in this form here, when we were naming our parts, let's do addition. Addition, we called the pieces of that add-ins and sum. In subtraction, we called it, I'm sure you remember this, minuend, subtrahend, and difference. Oh, those are fun words. And in multiplication, we called it multipliers and product. What would we call the f of x in a division sense here? Dividend, exactly. D of x. Another D word. Divisor. Q of x. Quotient. R of x. Remainder. They're no longer numbers, they are now expressions, polynomial expressions. F of x, D of x, Q of x, and R of x. Same thing with the other. The first of these is written basically horizontally. The dividend is the divisor times the quotient plus the remainder. That's how we used to check our division, remember? Multiply the quotient by the divisor and add the remainder to it. Written this way, it's more division. The dividend divided by the divisor yields the quotient plus the remainder over the divisor. Okay? So both of those are ways of expressing the division algorithm. Number 2 through 6 are fill in the blanks. In the division algorithm, which we just showed, the rational expression r of x over d of x is blank because the degree of r of x is less than the degree of d of x. Okay? A fraction. 1/2 would be this, 3/2 would not. Proper. Okay. The r of x over d of x is proper because the degree of r of x always has to be less than the degree of d of x. If it's not, keep dividing until you get that to be the case. Number 3. In the division algorithm, the rational expression f of x divided by d of x is blank because the degree of f of x is greater than or equal to the degree of d of x. Improper, exactly. Okay, number 4. A shortcut for long division of polynomials is blank blank, in which the divisor must be of the form x minus k. Synthetic division. Excellent. And Tef came in just at synthetic division. Okay. All right. Number 5. The blank theorem states that a polynomial has a factor x minus k if and only if f of k is equal to 0. The what? Okay, that was the next one. Notice the word right before x minus k. Huh? Yeah. Flip back to one page, and you see both names there. Which name shows up in number 5? Factor theorem. In number 6, the blank theorem states that if a polynomial f of x is divided by x minus k, then the remainder is r is equal to f of k. That's the remainder theorem. Very good. Now, I already assigned the homework, so I'll just say them again since we're here. Do number 7, do number 9, do any of the odds 11 through 23. Now, all the odds are at calccheck.com. Number 19 is at calcview.com. Okay? Do any of the odds 25 through 43. All of those are at calccheck.com, and 27 is at calcview.com. And Chris is here. All right. Do any of the odds 45 to 49. All of them are at calccheck.com. None of them are on calcview. Do either 51 or 53. They're both on calccheck.com, but 51's at calcview. Do any of the odds 55 to 61. They're all at calccheck. None of them at calcview. Do any of the odds 63 to 69. All of those are at calccheck. 63 is at calcview. Do any of the odds 71 to 75. They're all at calccheck. None of them at calcview. Do either 77 or 79. Both of them are at calccheck. Neither are at calcview. And then there's one word type problem, number 81. I would definitely try to do that one. Okay? Then you can look at the exploration. There's a couple of true false there, odd true false, 83 and 85. And then there's some think about it, 87 and 89. I'm not sure those answers are in the back, but if they are, think about it and see if you thought right. 91 is also a sort of interesting problem in exploration, and 93 is another think about it. All right, now, 2.4 talks about complex numbers. I used to teach this section, but I found it took time. It was in the course description. Nothing in there it mentions complex numbers. So basically, I'm just going to fly through it pretty quickly, just do a slideshow of it. Not going to be responsible for it on the test, but if you ever need it in subsequent courses, you'll at least be familiar with it. It's dealing with complex numbers. Now, in mathematics, especially higher level math, when we start talking about complex, that includes the possibility of imaginary numbers. Okay? Let's think back what we have started with. When you first began your mathematical career, one of the first things you did was count, right? 1, 2, 3, 4, 5. And we call those, that set of numbers you used to count with, and we still use to count with, the counting numbers. There is another name for it, and it's the natural numbers. The set of those, they're just the counting numbers, 1, 2, 3, 4, 5, 6, 7, and they go on forever in that direction. Okay? Later we added a little valueless number to that, 0, and we named a new set of numbers, the whole numbers. Okay? That was all the counting numbers plus 0. Okay? Those were the whole numbers. Then after a while, and this isn't probably the order you did it, we also included the negatives of those natural numbers or counting numbers. Now that set we called the set of integers, okay, positive and negative. And you had already run into some of these before, but you probably didn't call them this. When you started doing the ratio of two integers, we called those the first 5 letters, same as ratio. Rational numbers, okay? Now I said ratio of any two integers. That's not quite true, almost completely true. It's just that the denominator cannot be 0. Okay. So it's not any, the numerator can be any integer, the denominator can be any integer except 0. Okay? Now, that gave us rational numbers. A couple of things about rational numbers. You can always express a rational number as the ratio of two integers. Okay, that's its definition. The second thing, if you had that ratio of two integers and you decided to express that as a decimal number, can anyone tell me what the options would be for rational numbers? Say again? Okay. I'm not sure what you mean by that, but the options would be that either the decimal number is going to be finite, 0.5, 0.7238. You know, it ends, it terminates. Okay, terminating decimal. Or the other option would be that it repeats itself. That it repeats itself. I'm sorry. Okay, and that would be 0.333333333. It never terminates. Always repeats itself, or 0.874949494949. At some point, it starts repeating. They may be big groups of numbers or one single digit, but they start repeating, and then from that point on, they continue repeating. Okay. Now, those are the rational numbers, and Trey is here. Okay. What was the sort of the counter set of numbers to rational numbers? Irrational numbers. Now, how would you define those? Well, almost just what we just said in reverse. They are numbers that cannot be expressed as a ratio of two integers. Okay. Or they're numbers whose decimal representation never, ever repeats continuously. It may have a couple digits that repeat every now and then, but then somewhere else they never repeat at all. So, yes? Like pi. Okay? E. The square root of 2. The square root of 3. The square root of 5. The square root of 6. The square root of 7. The square root of 8. The square root of 10. There's tons of irrational numbers out there, okay? Now, if we combine the rational numbers with the irrational numbers, what do we call that set? Say again? Nope, not yet. Real numbers. That's the real number system, okay? The set of all real numbers. In other words, every little pixel on the graph can be represented by a real number. Rational number or irrational number. Every little thing on there is that. We call those real numbers. Covers everything on the real number line. Okay? Now, there are some things you can't express as a real number. Let's hit some of those. Okay? We'll use the imaginary unit I to write complex numbers. We'll add, subtract, multiply complex numbers. We'll use complex conjugates, it's a pretty good word there, to write the quotient of two complex numbers in standard form, and we'll find complex solutions for quadratic equations. We're really not going to do all those, but I'll show you how to do them. So let's start with the imaginary unit I, okay? Not a real number, an imaginary number. MIDI, right? Yeah. There you are. Okay. Anyone else come in? So it's just called roll. Okay. We have learned that some quadratic equations have no real solutions, right? Okay. You may have an equation there, and the graph of the equation may do something like this. Solutions are where they cross the x-axis or touch the x-axis. In other words, where f of x is equal to 0. That would be a solution. That would not have a solution. This would not have a solution. Okay? This would not have a solution if it never crossed the x-axis. Okay? So, here's one such equation. X squared plus 1 is equal to 0. Can you give me a real number that when you square it and then add 1 to it, you get 0? No, because any real number when you square it is going to be positive or 0. It could be 0. 0 squared is 0. That's a real number. But you add 1 to it, now that's not even 0. It's now positive. So this thing is always positive. So it can't equal 0. No real solution because there is no real number x that can be squared and then add 1 to it. Well, squared to produce negative 1. Because what they're doing here is subtract 1 from both sides. X squared is equal to negative 1. It's not going to happen, not with real numbers. To overcome this deficiency, mathematicians created an expanded system of numbers using the imaginary unit I. Okay? And here's how we define I. If you ever need it, if you ever see it, here's what it is. I is the square root of negative 1. Not a real number. You can't take the square root of negative 1 in the real number system, but we'll name that I in the complex number system. Now, another way to express that is square both sides of this, and what do you get? I squared is equal to negative 1. Can't happen in the real number system, but it does with the imaginary number. My wife had an employee once who was always talking about certain friends, and then Karen found out later she had never met some of them, so they were virtual friends, okay, sort of imaginary friends, like my big white rabbit or something like that. So, virtual friends are real creatures somewhere, but this is not a real number, it's an imaginary number, okay? By adding a real number to real multiples of this imaginary number, we now get the set of complex numbers that, it includes all real numbers and all numbers that have imaginary parts to them. So each complex number can be written in standard form a plus bi, where a and b are both real numbers. I is that imaginary unit. Okay? Now if the b happens to be 0, that's just a real number. If a happens to be 0, that's a strictly imaginary number. Okay? All righty. That's not all right. Huh? MIDI, I'm sorry. I said it wrong. Okay. I'm marked. There you go. All right. Anyone else coming since the cold roll? I got you, Mark. Okay. So, the complex number system includes all real numbers and all those that have imaginary parts to them. Okay? The sum total is called complex numbers. So we've been using complex numbers your whole life. Your accounting numbers are complex numbers. They're just with b is equal to 0. Okay? Now, if you had this, minus 5 plus the square root of negative 9, you know in the real number system you can't take the square root of negative 9. But you can break this down into the square root of negative 1 times the square root of 9, right? And what's the square root of negative 1? I. And what's the square root of 9? 3, so this becomes negative 5 plus 3i. Okay? And they just showed you how to do that. They put this 3 squared in front and negative 1 over there, and the square root of 3 squared. They didn't break this up like I would have. This would be 3i. Okay. Negative 5 plus 3i. Okay. So here's the formal kind of definition of a complex number. A and B, any real numbers. Any real numbers. Then the number a plus bi is called a complex number. It is said to be written in standard form if you put the isolated real part in front, plus or minus the part that has the imaginary unit in it. The real number a is called the real part, okay, of the real number, and the real number b is called the imaginary part. Now, I usually don't quite use that terminology. I say bi is the imaginary part, not just the number b, okay? It seems sort of bizarre to call a real number an imaginary part. It's imaginary because it's teamed with I, so it seems like to me this has two parts, real part, imaginary part. But they say b is the imaginary part, so I sort of differ with them a little bit there. When b is equal to 0, this is a real number. There is no imaginary part. But when b is not equal to 0, the number a plus bi is called an imaginary number. Okay? To me, I would call that a complex number, but imaginary number is fine because it does have an imaginary part. A number of the form bi where b is not 0, in other words, a is 0, that's called a pure imaginary number. It has no real part to it. Its only part is the imaginary part. Okay? So this is an imaginary number. This is a pure imaginary number. And what does that leave? A complex number. That's that. So you're calling this a complex number, and here they call it an imaginary number. To me, that's a little, I don't know, not quite satisfying. Okay. So, going back, the set of all real numbers is a subset of the set of imaginary numbers. I mean complex numbers. You have the real numbers that have no imaginary parts, and you have your imaginary numbers that have an imaginary part, where b is not equal to 0. These added together give you the complex numbers. Okay, so we've been using, like I said, complex numbers all along. This is true because every real number is also a complex number. Every imaginary number is also a complex number. But the real number can be written as a complex number as long as b is equal to 0. That is, for every real number a, you can write a as a plus 0i. Okay. Why would you want to? I don't think, but unless you're adding or doing something else to it, that you would need that imaginary part. All right. Now, again, we're not going to do much with this, but just so you'll know. Two complex numbers, a plus bi and c plus di. Both of those are complex numbers. They're written in standard form. Real part plus imaginary part. Okay? They're equal to each other if and only if a is equal to c and b is equal to d. Okay? Only if that's true. Okay? If this was 3 plus 2i and this was 2 plus 3i, those are not the same. The real parts have to be identically the same. The imaginary parts have to be identically the same. Sign and everything. Okay. So let's talk about some of the operations with complex numbers. And these are pretty simple. Okay? And I think pretty much like you would expect. To add or subtract two complex numbers, you add or subtract the real parts, and you add or subtract the imaginary parts separately. Okay? It's just like terms and unlike terms. You don't combine 3 and 4x. Those are two separate terms. All right. Happening? No, Courtney. Sorry. No, you're in here somewhere. There you are. All right. Anyone else coming into the call? Okay? So addition or subtraction of complex numbers for two complex numbers, a plus bi and c plus di, written in standard form, the sum of the difference are as follows. The sum, if you're adding two complex numbers, add the real parts, add the imaginary parts, and guess what? You get, in standard form, a real part plus a real times I. So that's your imaginary part. Similar way to do the difference, a plus bi minus c plus di, a minus c plus b minus d times I. Just, I think, like you would expect. You could think of this as distributing the minus sign across the parentheses. You just treat it like a binomial with two unlike terms, and you add them just like that. The like terms you add together, and you don't mess around with adding or subtracting if they're not like terms. All right? Done just the same way. All right. Now, the additive identity element in the complex number system is 0, same as in the real number system. The only thing you can add to any complex number and not change its value is 0. That 0, the real number is 0, okay? 0 plus 0i if you wanted to write it that way. Furthermore, the additive inverse of a complex number, a plus bi, would be minus a minus bi, okay? It's the number that's exactly the opposite of that. In other words, when you add this number and that number together, a minus a gives you 0, b minus b gives you 0, so you got 0 plus 0i, that's your additive identity, 0. Okay, and that's exactly what we showed you. A minus a is 0, b I minus bi is 0i, that's 0. Okay. Not something we use a whole lot, but perhaps. Now, we're not going to do example 1 necessarily. We'll just quickly do that. What would that give you? 4 plus 7i plus 1 minus 6i. Not that hard. Say again? Okay, this is a plus sign. 5 plus I, exactly. Well, they haven't finished. They'll get there in a minute. Well, it's taking them a while. 5 plus I, they finally got there. Okay? That's how you add. And similarly, you would subtract sign numbers. I guess this would be another addition. What would that be? 4. 4. Because your plus 2i minus 2i adds a 0. So you can add two complex numbers with imaginary parts to them and wind up with a real number, okay? If your complex part adds to 0, okay? If the imaginary part adds to 0. So that just gives you 4, okay? And that's in standard form. You don't have to write 0i. Perfectly all right to leave it just 4. Okay? Here's C. Okay? What would that one be? Whoa. What would that one be? Say again? What's your real part? Minus and minus 2 is? Plus 2 would be 0. How about your imaginary part? Is 0. And then you get a negative 5i. Okay? Now let's see what they did. They removed parentheses and did all that and grouped them, regrouped them together and got negative 5i. Okay, good for them. Okay. We're not going, oh, I guess there is another. Oh, no, not yet. Yes, there is another. Okay. So how about this one? Whoa. What we got there? Say again? It's just 0. Because your real part is 3 plus 4 is 7 minus 7 is 0. Your imaginary part is 2i minus I minus I. That would be minus 2i. 2i minus 2i is 0. So combine them all together and you get 0. All right, done. Any questions on that? Don't worry, you don't have to do these, but I just want you to be okay with them. You know, in case you ever run into them, you'll know basically how to do it. Now, many of the properties of real numbers are valid for complex numbers as well. Here's some examples. Associative properties of addition and multiplication. Doesn't matter, usually we talk with commutative, I don't know why there's different associative. Doesn't matter how you group them together. If you're going back to this one, you could have added these two first and then subtracted that from it, or subtracted this from that one and then added that to it. It doesn't matter how you group the numbers, you're going to come up with the same answer. That's the associative property of addition. We'll get it from multiplication as well, but it works there too. The commutative says it doesn't matter what order. If you're adding these two together, you could have added 4 plus 3 rather than 3 plus 4, and negative 1 plus 2 rather than 2 plus minus 1. It doesn't matter the order that you do it. It doesn't matter how they're grouped, and it doesn't matter the order, either for addition or multiplication. So that's associative property of addition and multiplication, commutative property of addition and multiplication. Distributive property of multiplication over addition. If you have something outside of parentheses times something inside, you distribute the outside over both terms of the inside. Okay? We will see that in small ways later. Okay? So notice how these properties are used when two complex numbers are multiplied. Now, you can do it this way and it's perfectly fine. But what would be a good way to use, a good technique to use? Say again? How about our good old FOIL? Exactly. These are always binomials, aren't they? Two terms, right? Or two entities there. So why not FOIL? Okay? Yeah, this is right. Everything's right about it. What's the first? AC. There's your AC. Okay? Plus ADI plus BCI. So that's AD plus BC times I. There it is. Okay? And then here you get, this is the only snag to this. Okay? When you multiply the length, what do you get? BD times, and what is I squared? Negative 1. Okay? So actually, these always condense to be a real number. I mean, a complex number. Because BD times the negative 1 is minus BD. So you have AC, a real part, and minus BD, a real part. And then you just add the imaginary parts, AD plus BC times I. So yeah, this makes it look real complicated. You just do it like you FOIL it. Just remember that last term, you always change the sign of this because the I squared is minus 1. Okay. Taylor? I'm sorry? Huh? Spencer. Oh, I missed you, Sean. I saw it. Okay. Sean, got it. Okay. I was looking through the people who weren't here and I just missed your name. Okay. Rather trying to memorize this multiplication rule, you should simply remember how to use distributive properties to multiply two complex numbers. I say it even easier. Just FOIL it. Okay? Remembering, though, that last term is always minus BD. Okay? The I squared is minus 1, so multiply the B and the D together and change its sign. Okay? Pretty easy to do. Okay? Let's distribute here. What would that give you? Negative 8 plus 12i. Always keep the sign in there. Negative 8 plus 12i. They go through a lot of, negative 8 plus 12i. Very good. All right, how about this one? What would that be? 8 minus 6. Very good, which would be 2. Okay. Here's the 8 part, and then the last part is the, wait, it wasn't minus 6. Minus 3. 8 minus 3 is 5. Okay, the real part is going to be 5. What's the imaginary part? Oh, that's your, yeah, say again. Okay. A negative 4i and a plus 6i, that would be plus 2i. So we had, what was the first? 5 plus 2i, I think. You don't have to rush it like I'm doing. It takes them a while to get there. Whoa, I missed it. Oh yeah, wait a minute. This is a minus 3i squared. That's a plus 3. 8 plus 3 is 11. No, 8 minus 3, because you have to change the sign of that. Fung is here. Okay, so don't rush these things. Take your time and do them. We're not doing them. I was just trying to rush it and do them. Okay, sorry. Okay, how about this one? This might be a little, oh yes, this one's nice. What's that one? Say again? Right? Oh yeah. Okay, actually you're doing, okay, 9 minus 6i plus 6i plus 4. 9 plus 4 is 13, because the i's disappeared. And look at that. 13. All right. Now, remember back when we were multiplying binomials? One of the real fun ones to do was a plus b times a minus b. And that gave us a difference of 2 perfect squares. Well, the square here is 9 minus 4i squared, which is plus 4. You can get there right away. Just remember, you always change the sign of that last one because I squared is minus 1. So sure enough, that's it. We have a name for this. They're going to give it to you later. But anytime you have a binomial, you keep the first term the same, and the second term is the same, except for a sign. We call that the conjugate. We didn't call it that when we did a plus b times a minus b, but that was a conjugate. When we were dealing with radical numbers, say 3 plus the square root of 2 and 3 minus the square root of 2, we called those the just went blank on the name. The radical, just the conjugate. We just called it the conjugate. They didn't have a special name for it. Now we're going to call this the complex conjugate. This is the complex conjugate of that. That's the complex conjugate of this. You just keep the first term the same and change the sign of the second. The complex conjugate or conjugate. Okay? And they're very handy things to use. You will keep using them your entire mathematical career because they're so handy to use. Okay? How about this one? Now, 3 plus 2i squared means 3 plus 2i times 3 plus 2i. So what would that be then? 9 plus 12i. 9 plus 12i. One more term. Minus 4. 9 minus 4 is 5 plus 12i. You got it. Okay? Takes them a long time to get there, but they got it as well. 9 plus 12i. Very good. Now this is sort of bizarre. When you square a complex number, you're going to get a complex number. Well, yeah, you always do. Okay? When you multiply a complex number by its conjugate, you get a complex number, but it's always totally real. This one has an imaginary part. So it might seem a little counterintuitive, but it does work. So now they get around to telling you about these complex conjugates. I already did with that example 2c that the product of two complex numbers can be a real number, and that occurs when the pairs of complex numbers of the form a plus bi and a minus bi, called complex conjugates of each other. If that would have been a plus the square root of b times a minus the square root of b, those are conjugates of each other. A plus b times a minus b, those are conjugates of each other. All of those have some nice special qualities, but these are complex conjugates. And when you multiply those together, you've already done so, square the first, that's a squared, minus bi minus abi plus abi, that adds to 0 every time, okay? Minus b squared, I squared, but I squared is -1, so that comes up a squared plus b squared. And guess what, team? Remember when we used to say you can never factor the sum of two perfect squares? You can factor the difference of two perfect squares. That gives the conjugates of each other, all right, of their square roots. But now you can factor the sum of two perfect squares. It's a plus bi times a plus bi, a minus bi, because that gave you the sum of two perfect squares, okay? So you can't do it in the real number system, but you can do it in the complex number system, okay, with imaginary parts. We're not going to do that, but you can now, okay? To write the quotient of a plus bi and a minus, a plus bi and c plus di in standard form, where c and d are not both 0, okay? You can't have this thing being, if you're doing a quotient of this and that, this thing can't be 0. C could be 0 as long as D's not, D could be 0 as long as C's not. Or neither one can be 0, but they both can't be 0, okay? Then what we do, we don't really have a division for complex numbers. So, and I don't know if you remember back to your radicals. It's really hard to divide radicals. How did we do that? You remember? Let me do a little bit of, I don't know if you remember it or not, but let's do it, okay? Give me a number, any number.
3.
Second?
3.
7?
3.
3, okay, 3. You want a plus or a minus? Plus, okay? Give me another number. 2. I'm going to put the square root of 2, divide that by, give me another number. 4. Plus or minus? Minus. Another number, huh?
6.
I can't hear. 6. The square root of 6. Okay? Now, do you even want to try dividing those two numbers? Because remember, square root of 6 is an irrational number. If you started writing its decimal representation, you go on forever and never develop a pattern. Ever. You can't write that as a rational number. You can't write it as a fraction. Ever. Okay? So, this number, the best you could do would be approximate it with a bunch of digits after it. And then divide that into another number approximated with a bunch of digits. And you're still going to get an approximate answer. So what's the technique for dividing these two? Yes, multiply the denominator by its conjugate. Absolutely. And that would be, what is the conjugate of 4 minus the square root of 6? 4 plus the square root of 6. But if you multiply the denominator by that, what must you do? The numerator by the same entity, 4 plus the square root of 6. And why can you get away with that? What's 4 plus square root of 6 over 4 plus square root of 6? 1. And when can you multiply 1? Anytime you want to. It doesn't change the value at all. All right, what does that give you when you do that? The numerator becomes a little bit of a mess, but we can live with it. FOIL it. 12 plus 3 root 6 plus 4 root 2 plus, say again, square root of 12, okay? You can multiply under the square root, okay? This is a 6 there, it's a really ugly 6, okay? Now, how about that denominator, though? 16. Say again. Minus what? Okay. All right, if you're calling it, that would be 4 times 4 is 16. That would give you plus 4 root 6 minus 4 root 6. Add to 0. That's the magic of multiplying by conjugate. The middle terms, the cross terms disappear. And then what do you get at the end? Second? Minus 6. You're absolutely right. 16 minus 6. Now what does your denominator become? A whole number. A rational number, not an irrational number. So you have, and this, the top is a mess, I admit it. Yeah, it's definitely a mess. But it's 12 plus 3 root 6 plus 4 root 2. And if you remember, we tried to pull out a perfect squares, so that would be plus 2 root 3, okay, over 10. Well, guess what? You can approximate this and that and that. Yeah, they're a mess. Add them together and divide by 10. I can divide by 10 really easily. Move the decimal one place. That's it. That's 1 plus this one. And that's all. Okay. Doing it that way? Ooh, no. No, no, no. That takes forever. Okay? Doing it this way, it's okay. Okay? Once you've added this together. Well, same thing here. Let's erase all this. Well, where is it? I hit the wrong button. No, I didn't. Here it is. There we go. Okay. What we do is, don't try to divide by imaginary parts. I don't even know how to do that. But multiply the denominator by its conjugate. But of course, you have to multiply the numerator by the same conjugate. Not by its conjugate, by the denominator's conjugate. Because this has to be 1. Okay? And this is sort of a mess, but it's a doable mess. A times C plus B times D. Remember? That's how we multiply those. Plus or minus AD plus B. So BC minus AD times I. Okay? But your denominator, there's where the magic happens. C squared. And these terms cross out. Add to 0 plus D squared. A perfectly fine real number. Okay? And this is a perfectly fine complex number. It just looks messy because you have all these letters in it. So that's a number times I. Okay. In standard form. Okay. Now, they usually do one more step, unfortunately. Oh, no, they don't. Okay. So, if you were doing this problem, what would you do? Say again? Yes, and what is the conjugate? 4 plus 2i. So multiply the denominator and the numerator by 4 plus 2i. Now, actually, something I would do first, although I'm really lazy, I would have factored out a 2 here. Just had the 2 on the outside, then multiply by 2 plus I. It'd be a little bit easier. It's not hard this way. Why in the world carry around extra factors and make the numbers bigger? I'm too lazy for that. Okay? But anyway, so this up here, even though it might look complicated, that would just be 8 minus 6. You're absolutely right. So that'd be 2. And then you'd have plus 4i plus 12i, that'd be 16i. 2 plus 16i, and then guess what? The 2's are going to cancel out, and this would just be 16. Yeah, the cross terms are going to cancel out, and what will this be? No, 16 plus 4, 20. Okay, your denominator would be 20. Okay. Now, they're going to do all that and 2 plus 16i over 20. Then factor out your 2's, okay? Such a mess that if it had just factored out 2 in the beginning, you would have had this taken care of, okay? That would be, and here they do it. Now to write it in standard form, this isn't quite standard form. You do 2 over 20, which is 1/10, plus 16 over 20, which is 4/5 I. So 1/10 plus 4/5 I. Real number plus real number times imaginary unit. That's standard. Don't sweat it. We're not going to have these, but you know. So, complex solutions of quadratic equations. Okay. And one reason we're doing this is that in the next section we're going to hit some of these. I'm going to try to avoid them on the test just so you'll know that they're coming. Here's what you do. You can write out a number like the square root of -3. That's not a real number. So how would you write that in standard form? No, the square root of 3i. Okay. I like to write the I in front. I times the square root of 3. Okay? So I'll factor this into -1 times 3. Square root of -1 is I, and the square root of 3 is 3. Now, I know their standard form says you write the real part and then I. I do not like to do it that way because in print, yeah, you can tell that square root sign ends right there. But if you got a little extravagant with that line there, then you can't tell if that line's over the I or not. Is that I in the radical or not? So that's why I always put the I in front, because it removes the ambiguity. There's nothing wrong with removing ambiguity. So the number square root of 3i is called the principal square root of -3. Okay? And I would say I root 3. Okay? The principal square root of a negative number, when a is a positive real number, the principal square root of -a is defined as I times root a. That's what I would say. They call it the square root of a times I. Okay? You just have, even when you read it this way, the square root of ai. Are you meaning square root of ai or square root of a times I? If you put the I in front, even when you're reading it, I times root a. No ambiguity there at all. Okay? So even though this is clear, when you're reading it, it's not clear. Okay? If you say the square root of ai, well, is that I in the radical or not in the radical? It's not clear. If you say I root a, perfectly clear. Okay. So if we were going to solve this, what would you do? You think you can factor? I don't think so. No. So you would use the, can't factor, you usually use the quadratic formula. Now, remember, you have 3 cases of what you can come up with a quadratic formula, all depending on that little thing called the discriminant, right? What's that discriminant? Anyone remember? In the quadratic formula. Yeah, b squared minus 4ac. Let's do it right now. What is your b squared here? It's 4, right? Okay, all right. Minus 2 minus 4ac. That'd be minus 4 times 3 is 12 times 5 is 60. 4 minus 60. Guess what? Negative number. In the radical, you're going to have a complex answer. Okay? So that's, without figuring out what the answer is, you can look at this, use your discriminant, b squared minus 4ac, see if that's going to be a real solution or a complex or a solution with an imaginary part. Okay? This one will have an imaginary part, and that's exactly what we did. I just didn't do the first part. Minus b plus or minus the square root of your discriminant, b squared minus 4ac, divided by 2a, and that gave you positive 2 plus or minus the square root of negative 56 over 6. Okay? Now, what would you do from that point? Yeah, pull out the minus here and put an I in front. That's exactly what I would do. Now, the 56, I would look at that and say, Is there a perfect square somewhere lurking inside 56? 4. 4 times what?
14?
Yeah, 4 times 14. So that would be 2 plus or minus 2i, because the square root of 4 is 2. So 2i times the square root of 14 over 6. Well then, all those are even, so divide, so this will be a 3, that'll be a 1, and that'll be a 1. So it'll be 1 plus or minus I root 14 over 3. And then they'll write that in standard form. Okay, that's exactly what we said. And in standard form, this will be 1/3 plus or minus root 14 over 3 times I. Now that one, yeah, you can probably get away with the I there. It's a lot clearer. The square root of 14 over 3 times I. I still kind of like to put it in front, because when I'm reading, I say I times root 14 over 3. There's no ambiguity. When you say square root of 14 over 3i, well, is I down here with the 3? No, it's not. It's over there. So writing it is pretty clear, but saying it, that's why I still like to put the I in front. They don't like to because it's not standard form. Okay. And that was the last slide. So you're not responsible for that, but you will see things about that in the future. Okay? So let's move on to 2.5. Why did it do that? Now I've got to start over again. Yeah. Okay. Sorry. Two 5. All right, don't have a lot of time, but we have a little bit. What's that? Okay, what do you say?
You just string 3.
Oh, no, I have to wait until it boots up here, and then I have to do slideshow from current slide or from beginning, one or the other. Then it comes up. My computer didn't go through all that. This one does. Okay. So we're still in polynomial rational functions. And by the way, this is the last section on the polynomial part, because section 2.6 is the rational part. So we're talking in 2.5 zeros of polynomial functions. Okay? What we'll do is use the fundamental theorem of algebra to determine the number of zeros of polynomial functions. We'll find rational zeros of polynomial functions. We'll find conjugate pairs of complex zeros. We're not going to focus on that, but we'll talk about it. And we'll find the zeros of polynomials by factor. Okay? We'll also use Descartes' rule of signs and the upper and lower bound rules to find zeros of polynomial, and we'll find zeros of polynomials in real-life applications. The one thing, this one right here, find the rational zeros of polynomial functions. That's using a technique called the rational zeros test. I wish they would have actually said that, but it doesn't matter, but we will do that. Okay, so let's start with the fundamental theorem of algebra. That sounds pretty impressive, doesn't it? In the complex number system, every nth degree polynomial function has precisely n zeros. Now, how is that different from what we're talking about in real zeros?
Say, like if we got some square root 2, I mean not square root, to the second power or third power, it's just saying how many zeros you can have.
Right, and you can have up to that level, right? If you have a 5th degree polynomial, you can have up to 5 roots. You may not have 5, but you can have up to 5. Once you have 5, you can't have any more. In the complex system, you have exactly n zeros, or n roots. But some of those could be complex. And that's exactly what we ran into before. If we had a 5th degree polynomial, you might wind up with only 3 or 4, 2 or 1. always would have at least one real zero. Okay? The rest of them could be complex. There could be some that are multiplicity. Okay? So this is an important result. This important result is derived from the fundamental theorem of algebra, first proved by German mathematician Carl Friedrich Gauss. You talk about pretty impressive characters in mathematics. This was one. Of course, Newton rates really high. He developed calculus. Leibniz did too, so he rates fairly high. Way back in antiquity, Archimedes did some amazing things without calculus, but actually was using a lot of the same principles of calculus. So he is a pretty great mathematician. And usually after those, Gauss is listed as almost the next. Really impressive. He was the first of the great German mathematicians, and boy, they had a lot to follow him. The fundamental theorem of algebra says if f of x is a polynomial function of degree n, as long as n is greater than 0, okay, then f has at least one zero in the complex number system. That is really understating what it said here, isn't it? This says you have precisely n zeros. But the fundamental theorem of algebra says it really cheaply has at least one zero in the complex number system. And this up here says, well, you have more than one. You have n. Whatever n is, that degree is, you have that many zeros. Okay? So this was a pretty, it seems like a pretty weak theorem, but this took a lot of effort to prove. And Gauss did it. Okay? So using the fundamental theorem of algebra and the equivalence of zeros and factors, you can obtain the linear factorization theorem. This says it a lot better. If f of x is a polynomial of degree n, of course n has to be greater than 0, then f has precisely n linear factors. Okay? So f of x could be some constant a sub n you can pull out front, and then x minus c1, x minus c2, x minus c3, all the way up to x minus cn. Okay? Exactly that number of factors. Now, we didn't used to call them c's, did we? A's or b's or something like this. The reason they call them c's were these c's now can be complex numbers. If these were real numbers, no, you wouldn't have exactly that many, because some of them might not happen. In complex numbers, yeah, you have precisely. Remember, complex numbers can be real. Okay? That's why we had to do the last section, just so you can get that. Okay, note that the fundamental theorem of algebra and the linear factorization theorem tell you that tell you only that the zeros or factors of polynomials exist. It doesn't tell you how to find them. Boo yes. Okay? It just said, yeah, they're out there. Now you go find them. Okay? Such theorems are called existence theorems, and they're usually pretty hard to prove, but because you don't actually find the things, you just have to prove they do exist. They're simple to state sometimes, but pretty hard to prove. All right, here's example 1. Yeah. First degree polynomial function, f of x equals x minus 2. How many zeros do you think it has? 1. And what would that zero be? X equals 2. Exactly. Okay? Because that's the first degree polynomial, it has to have one complex zero, and because set it equal to 0, add 2 to both sides, x equals 2. It has a complex zero, it just happens to be a real number. Okay? So that one's pretty easy. Okay? How about this one? Counting multiplicity, the second degree polynomial function has how many? 2. Has to have. And this happens to be a perfect square trinomial. So what would its factoring be? X, right? No. X minus 3 times x minus 3. So its two zeros are x equals 3 and x equals 3. Okay? It's a multiplicity. So that does count as 2 because it does have 2 factors. They just happen to be the same one. X minus 3 times x minus 3. So you're absolutely right. Has exactly 2 zeros. They look alike, x equal 3 and x equal 3, called a repeated zero multiplicity of 2. Okay. Let's see if we can squeeze this one in. Third degree polynomial function. How many zeros in the complex number system? 3. How many in the real number system? Well, what would be the first thing you'd do? If you set that equal to 0, what would be the first thing you would do? Say again? Okay, wait. Factor! X times x squared plus 4. Okay? You set it equal to 0. That's what I was going to say first. To find the 0, set it equal to 0. Factor it, and you have x equals 0. There's a real 0, but what happens when you have x squared plus 4 equals 0? You're in the complex numbers. Plus or minus 2i. You don't need to go there, but the other 2 are complex. All right. Just to show you, they did the same thing we did. Let me erase all this. Okay. And they came up with 3 factors, which gave you 3 zeros. Okay. We'll start next time with the rational zeros test. Let's see, homework exercises here. Let's see, are there any? I think we got a few done. Do any of the odds 9 through 13. Yeah, we'll stop there. Okay. If anyone did not get your quiz, get your quiz. Did anyone not get a quiz? I know Colby. Anyone else? You didn't get one? All right. Do you need graph paper?
Oh, no, I didn't.
I'll get that.
Do you need graph paper? Okay, you do. Okay. It's graph paper. Here we go. Quiz. So I took the one you did these. Need a quiz. Need graph paper? Okay. Graph paper. Need graph paper? Okay. There you go. Good deal. We'll see you Thursday.